So the LHC is basically the most fundamental of experiments. It's like what any child would design as an experiment. You take two things and you smash them together. And you get a lot of stuff that comes out of that collision, and you try to understand that stuff. Now, in this case, what we're smashing together is tiny protons, which are inside the center of every atom. And in order to get them going as fast as possible, we have to build this huge 17-mile ring. And we run those protons around the ring multiple times to build up speed, almost to the speed of light. And then we collide two beams going in opposite directions at 4 points. And at those 4 points are 4 different experiments: ATLAS, LHCb, CMS, and ELISE. Now I work on the ATLAS experiment. And ATLAS is like a huge 7-story camera that takes a snapshot of every single collision. And that's billions of collisions. And the hope is that we'll see the very famous Higgs particle. But every time we've turned on a new accelerator at a higher energy, we've always been surprised. So the real hope is that we'll see the Higgs, but that there's also something amazingly new.
We study particles because just after the Big Bang, all there was particles. And they carry the information about how our universe started and how it got to be the way it is and its future. At the beginning of the 1900s, it became clear that all known matter, everything that we know about, is made of atoms. And that atoms are made of just 3 particles: the electron, the proton, and the neutron. In the 30s, other particles were discovered. And by the 1960s, there were hundreds of new particles, with a new particle discovered every week, and there was mass confusion. Until a number of theorists realized that there was a simple mathematical structure that explained all of this. That most of these particles were made of the same 3 little bits we call quarks, and that there are only a handful of truly fundamental particles which all fit together in a nice, neat pattern. And there was born the Standard Model. Eventually, all the particles in the theory were discovered, except one, the Higgs. And the Higgs is unlike any other particle. It's the linchpin of the Standard Model. Its theory was written down in the 1960s by Peter Higgs and a number of other theorists. We believe it is the crucial piece responsible for holding matter together. It is connected to a field which fills all of space and which gives particles like the electron mass and allowed them to get caught in atoms, and thus is responsible for the creation of atoms, molecules, planets, and people. Without the Higgs, life as we know it wouldn't exist. But to prove that it's true, we have to smash particles together at high enough energy to disturb the field and create a Higgs particle.
One of the most basic facts about the universe is that it's big. So you might wonder, why is the universe big? There's actually a single number called the cosmological constant that plays a crucial role in determining what the universe looks like. In fact, around 10 years ago, astronomers discovered a really remarkable fact. The universe is getting bigger and bigger at a faster and faster rate. But this rate is a million, billion, 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 billion times slower than what we'd actually predict. When you're off by a factor of a million, billion, 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 there's something very wrong with your understanding of basic physics. Even worse, this one number, the cosmological constant, needs to have this extremely precise value. And if the value is different even by a tiny bit, we would radically change what the world looks like around us. If you saw a situation where if the parameter has a very dangerous value and you change it a little bit, the world would change radically and we'd be dead, we couldn't possibly live, you would wonder where that came from. How is that possible? There is a scientific alternative to believing there's someone out there who loves us, twiddling the dials very finely for things to work out. And this alternative, said briefly, is that everything we see in our observed universe is actually a very small part of a much, much vaster multiverse. You might literally imagine that from some bird's eye point of view, if you went to enormous distances, you would see that our universe is actually a little pocket inside a vastly bigger space. In this picture, these mysterious numbers, like the cosmological constant, are actually basically random. And out there in the multiverse, next to us somewhere, is another region where these numbers take on some other random value. And then another region where they take on some other random value still. Only in a tiny sliver, minuscule part of this gigantic multiverse, for completely accidental reasons, do these numbers take on the very, very special values which allows structures to grow, stars to form, galaxies to form, ultimately things like us to form.
Plot here. Now the grand combination.
Here goes.
So this distribution is extremely clean, except one big spike here in this region here. Excess with a local significance of 5.0 sigma at a mass of 126.5 GeV.
As a layman, I would now say, I think we have it. Okay.
Peter is there.
Yeah, you get Peter. Peter's there. Peter.
Well, I would like to add my congratulations to everybody involved in this tremendous achievement. For me, it's really an incredible thing that has happened in my lifetime.
Not only in your lifetime, Peter.